Yeah, welcome everyone. So coming towards the your doubt, Sean, the excess pairs are like you can clearly see here. If you consider only four links, number of pairs are four. So, but as you increase the number of links, number of pairs are not equal to number of links. They are more than that. So, for six number of links, you will get seven pairs, and to have 1 degree of freedom you have to make seven pairs. Okay, that is the meaning of it, and it means we have to make one excess pair. Okay, so if it is a 6, then we will say it's a zero excess pair. Number of links and number of pairs are same. Okay, and similarly if you again increase n to 8, number of pairs are not 8, they are 10 now. So here we have two excess pairs. So um, the conclusion out of it was, if we want a mechanism with a single degree of freedom, and we increase the number of links from 4 to higher number, the number of pairs will not increase in that fashion. What will happen? Let's say 4 6 8, number of pairs will not increase as 4 6 8, they'll increase as 4 7 10. At every step we are going to add one more excess pair. Okay, so one excess pair in the one more extra pair, you can say, so as to maintain the single degree of freedom. So that is the idea. Here we have zero excess pair because four links and four pairs are there. But as we go on as we go on increasing the number of links, our pairs are also increasing. Okay, so that is the whole intention behind it. Is it clear now? Yeah. Okay. So coming towards the next points about this topic, before we jump into the um, slider crank mechanisms, let's try to understand some basic terms. The two basic terms you should know is mechanical advantage and transmission angle. Okay, so mechanical advantage is nothing but the ratio of output torque to the input torque. Okay, at any instant, you can say. So whatever power, so if you suppose this is a mechanism ABCD, AD link is fixed, and if you assume that there is no friction and inertia, okay, there is no friction in between the uh, joints, and there is no inertia force. If you ignore these two things, and if you are, so then what we can say that whatever power you are giving as input, okay, the power input means torque into the velocity at input link. Suppose assume this as your input link. Okay, so this is your input, whatever you are giving here, and you'll get, accordingly you'll get the output. So input power equal to output power, if you do, you will easily get the ratio of output torque to the input torque. So write down definition. Mechanical advantage is nothing but the ratio of output force or torque to the input force or torque. Okay, so it's a T4 by T2. Another definition, which you should know, is the transmission angle. This they can ask in exam. Okay, so like in a mechanism we have a crank. This is the crank. Okay, the link with the shortest link, we call it as a crank, and this is, for example, you can call this as a crank or input link also, you can call it as. the C is, let's say, output link, or rocker you can say, and the link which joins input and output link, we call it as a coupler. Correct? You are aware of this terminology: crank, coupler, rocker, input link, output link. So the angle between output link and coupler is called as transmission angle, and that is given by mu. Okay, so the definition is angle between output link and coupler is transmission angle. Can you tell me, like, uh, when there is a chance of getting maximum transmission angle? And when we will have the chance of minimum transmission angle? Can you think of such situations for this particular diagram? So for this figure which I'm showing here, can you think of the cases where there is a chance of getting maximum transmission angle and minimum transmission angle? Yeah. So A and D are in opposite direction, correct? So if you bring this B point here, okay, uh, then you can clearly see there is a chance that um, you will end up with the maximum angle. Okay, then you will end up with the maximum angle. And yeah, so correct, theta equal to 180, in other words. So corresponding to theta equal to 180 degree, you will get a uh, mu max. And at what angle you will get mu minimum in this particular case? When your theta is correct. Okay, because at that particular point, you will have, I'll just try to show you how this diagram will look like roughly. Not may not be exactly same, but I'm trying to explain this. So this is the case of link A, link D, B and C, and this is your mu max. Okay, try to think of this situation. And this is uh, okay, I'm trying to draw it. So this is link D, at bottom link A here, B and C. So this is your mu minimum. Okay, try to think of these situations. Yeah, so in first case we have theta equal to 180 degree, and here theta equal to 0 degree. Okay, so basically you are creating two different triangles basically. Okay, so whenever this um, the structure with the four sides converts into a triangle, we will end up with the either minimum transmission angle or the maximum transmission angle. Okay, so you should know these um, values of theta at which we will get the mu max and mu minimum. Okay, any doubt till this? So can you think, can you tell how you will calculate? So this is there, but how you will proceed after this? So how you will calculate mu max if I give you this triangle? Okay, the triangle sides are given to you, A, B, C, D. You are aware of this A, B, C, and D. Can you tell me how you will calculate this mu? Yeah, you can use sine rule also, correct? That is fine, but you don't know other angles, right? uh yes, so what we can use is, yes, cosine you can use, like so in this case I'll just try to explain you here. A plus d whole square will be equal to b square plus c square minus 2bc cos of mu. Okay, and this mu will be mu max in our case. Okay, so this logic you can apply, and in this situation what you can say, d minus a whole square equal to b square plus c square, same formula. Okay, nothing is different in this situation, minus 2bc cos of mu. Okay, so same formula, but actually your triangle, the side of the triangle here is d minus a, and in this first case it is d plus a. That is the only thing which is changing, but ultimately I'm using the same formula. Okay, is it clear till this? Will you be able to solve questions when I give you for solving? Yeah, okay, good. So yeah, as if now try to understand this theoretical part, and then later we'll solve questions on it. Can I proceed towards next slide? Okay, I'll explain once again. Yeah, just give me a minute. So I hope your doubt is about the minimum and maximum angle, right? Transmission angle. Yes. So this mu is this transmission angle. Okay, mu is angle between coupler and output link. Under which situation we will get the maximum value of mu and minimum value of mu. That is what I am trying to calculate. Means what maximum value mu can take and what minimum value mu can take. Okay, so the range we are trying to calculate here. So if think that you are pulling this point on left hand side. Okay, so this link A will come here, the C point will come here somewhere, and then your uh, basically structure will look something like this. Okay, so this is your B dash point and this is your C dash point. Do you agree if I bring this point C on left hand side, if I rotate it towards left, do you agree that this C can come somewhere here, and B C will come to C dash and B will come to B dash? Yeah, so this is the maximum possible angle, right? Because even after that, let's say comes down, what will happen? This angle is gonna decrease again. Okay, it will not increase. So that is the reason we said that this is the maximum value which you can get. Okay, so this is the final figure which I have shown you in order to explain this point. Coming towards the minimum case. Okay, let me try to draw this point C and B again. So if I'm bringing this B point somewhere here, okay, so the B is, I'm bringing this B to here, let's say B dash. Then what will happen? This C will come somewhere here, okay, or let's say yeah, somewhere here the C point will come, C dash, and then this is your BC link. Okay, so this is how your structure will look like: A link, B dash, C dash, and D. Okay, um, Do you agree that we can achieve this kind of position? Sorry. Mhm. Yeah. So, and there is no other possible way to get the minimum angle than this. So this is this angle here, angle B dash C dash D. Okay. So I will explain here again. This angle is the minimum possible angle which we can get whenever we are calculating the angle between output link and coupler. Because if you rotate this further down, this angle is increase again. Okay. So ultimately, this is the lowest possible angle. Okay. I hope it's clear now. Yeah. Can I proceed to next slide? Okay. So now let's try to understand some basics about the slider crank chain. In the beginning of the last class, I told you that slider crank is a mechanism used in IC engine. Our first link is frame here. Okay. Overall frame and guide wedge. Second link is crank. Third link is connecting rod, and the fourth link is a slider, or you can call it as a piston. Okay. And this mechanism we use in like IC engine, reciprocating compressor, or um, reciprocating pumps, you can say. Okay. So the application of this, okay, whenever you are fixing first link, we call it as a first inversion. Okay. First inversion in the sense it's like we are um, trying to see what other mechanisms we can build out of it, or what other things we can build out of it whenever we fix different links. You remember, uh, I have explained you 4-bar chain. If I put fix the short link, what I get. If I fix the link opposite to the shortest link, what I'll get. If I fix the link adjacent to the shortest link, what I'll get. We have seen like different mechanisms will get, like crank, rocker rocker, crank rocker. Okay. So same thing here. um, Suppose if we fix first link in slider crank chain, what we are doing in 4-bar chain, we are just replacing one link by slider. We will get a slider crank mechanism. Nothing is different. Okay. Just like, for example, this link is fixed. So what you do, this fourth link you replace slider, you will get this. Okay. So if you just replace this link with a slider and attach it, you will end up with a slider crank chain. Okay. And now I'm fixing first link, and that's why I'm calling it as a first inversion. Okay. Different mechanisms we can obtain by fixing the different links of this slider crank chain, and we are calling it as a inversions. Okay. So first inversion will look like this, and the application of this we will do in reciprocating engine, compressor, pumps, etc. Okay. Reciprocating engine like our IC engine which we use, and reciprocating compressor. Okay. In these kind of applications, we use this mechanism. Okay. So link 2 is crank, 3 is here connecting rod, and link 4 is slider, and link 1 is our um, guideways and support system, fixed support system, which is fixed. Okay. What will happen if I fix the link 2? What will happen if I fix crank itself? What will happen if I fix the connecting rod? Okay. Or link 3? And what will happen if I fix the slider itself? So that is what we are going to study in upcoming slides. Is it clear till this? Any doubt? till this point? Yeah. So in the first inversion, we are fixing first link. In the second inversion, I am fixing now second link. Okay, so this was our first inversion. What we are doing is we are converting the first inversion to second inversion by changing the link which is to be fixed. Okay, so here now I am fixing link number 2. Structure will, I'm just, and we have just rotated the structure, but ultimately you can clearly see nothing, everything is same except rather than fixing link 1, we are fixing link 2. Link 2 is fixed. Okay, then we call it as a second inversion. The reason behind drawing it like this is to explain you the applications of it. Second inversion we use in Whitworth quick return mechanism. Do you know in which application we use this Whitworth quick return mechanism? Yes, in shaping machine, we do this. We use Whitworth quick return mechanism. Why? Because we want that in case of shaping machine, that during the forward stroke, okay, during the forward stroke, um, the material has to be we are cutting the material, okay, and that's why the forward stroke is a bit uh, slow compared to the return stroke, because in return stroke we are not cutting the material, it's a idle stroke. Okay, so what we want is we want a mechanism in a such a way, it will work in a such a way that in forward stroke it will take a bit more time compared to a return stroke, because in return stroke there is no work done, or there is, it's just an idle stroke, we are not removing any material. So with what quick return mechanism, you already know that it is used in shaping machines, correct? And another application of this is rotary engine. Okay, so I would suggest you to remember this applications of different inversions. You may get in match A and B kind of questions. Okay, so look at this particular exam figure here. Figure number C explains you the overall working of Whitworth's quick return mechanism. So I'm trying to show you here two different angles. So how the time is linked with those angles, that I'll explain. Okay. So time for cutting, we want time for cutting to be more than time for return, right? Time for return. We want time for cutting to be more than time for return. Let's say time for cutting is theta, and beta is, let's say, the theta and beta are two different angles. So all the angles are from C, sorry, B dash. This is B dash. Okay, I'll use the red pen here to show you the angle. B double dash A B dash. So at this, so this B double dash A B dash creates two angles. One is this obtuse angle it will create, and it will also create one acute angle. Okay, so the obtuse angle, the bigger angle which is getting created here, we are calling it as a theta. So theta is b double dash a b dash obtuse angle, and beta is b double dash a b dash acute angle. Okay, so no need to draw this figure, you will get it anywhere. So just write down this what is meant by beta and theta. Okay. 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 Uh, is it clear till this? Okay. Yeah. Another example here that we could give you is um, a rotary engine. So you can clearly see this mechanism. I'll try to draw here again. Um, so we are fixing the crank, and okay, so the same thing. Um, link number 1, 2, 3, and 4. So the part of this is here actually in the um, rotary engine. So you can clearly see this is link 3, link 2, which is fixed. Link 1 is actually this one. Okay. Um, so this link 1 is this, basically the support system, and here this is link 4, which is um, you can say a slider. Okay. I hope but overall this is the same structure. As we have many such arrangements. Okay, so for example, this is a 9-cylinder engine, so we have 9 such arrangements. That's why we made a single frame. Okay, and hence this entire link is link number 1. This will be link number 1. Outer boundary will be link number 1 for all these setups, and then individually we will have um, link 2, which is link 2 is also common, which is fixed for all. Okay, link 1 is common for all, but we just have different connecting rods and sliders. Okay, and that's how we can make a rotary engine out of it. Here link 1 and 2 is common, the rest of the links are um, different. Okay, can I proceed towards next slide? Yeah, in the third inversion what we are doing is we are fixing the connecting rod. Okay, so here third link is fixed. Third link is fixed. So in this case, third link means our connecting rod. Um, so this is, let's say, a basic structure, how it will look like. And the applications of third inversions is oscillating cylinder engine. And the second application of this is crank and slotted lever mechanism. Okay. Okay, so here this is more or less similar to the our quick return mechanism. Okay, but um, here we are fixing the link number 3. Okay, I'm explaining about the crank and slotted lever mechanism. This is more or less similar to what we have studied previously. So here also you can clearly see this is the setup. Link 3 is fixed. Let me use the laser pointer. Link 3 is fixed. Okay, I'm just inverting this so you can imagine that this is our mechanism here. And for to the link number 4 itself, we are attaching one another link, fifth link, and we have attached a cutting tool to it. Okay, so basically um, you can just ignore this part. This is an additional part to this to make this slotted slotted lever mechanism to work. But ultimately, if you focus on this part, just link number 1, 2, 3, 4, the as you rotate the link number 2, it will rotate like this. And again, about this point A, it creates an obtuse angle and acute angle. One obtuse angle on top and the acute angle on the bottom side. Okay, so basically the time for forward stroke is given by theta, and then time for return stroke is again given by beta. So it's more or less similar to that, but in order to achieve it, what we have to do is fifth and sixth link we have to add. Then this mechanism will work like a quick return. Okay. The another example of this inversion is we can apply in oscillating cylinder engine. The figure B here extends the oscillating cylinder engine. Okay, link 2 and 1 as it is. So at the end of link 1, we have connected the um, basically we have connected the piston. So piston is fixed to the link 1. So you have to assume this entire thing as link number 1, including piston. Okay, and then we made the link 4 as a cylinder in the cylinder form. Okay, which is hinged at one particular point, and then this is how this mechanism will work. Okay, so as you move this um, link number 2, as you rotate this crank, the link number 1 will just move up forward and backward, and in the meantime, like, this piston will little bit oscillate because it is not completely fixed. It is hinged at point B. That's why we call it as a oscillating cylinder engine. Okay, so you should know these two applications for third inversion. In exam, you should not mix up this applications. Okay, so you have to be very clear that which application belongs to which inversion. Can I proceed towards next slide? Okay. This is the last inversion, which is fourth inversion. We are fixing fourth link. Okay, so indirectly what we are doing, we are fixing the fourth link means slider. So assume this is your fixed fourth link. Okay, so this is the fourth link, which is slider, but we are extending our slider and giving a shape of a hollow cylinder to it. Okay, so this is a part of slider. This is part of fourth link. Okay. We are extending it to make a hollow cylinder, and to link number one we have rigidly attached this piston. So this piston is part of link number one itself. So this entire is your link number one, which is in blue color. Okay, this is your link number one. Then we have link number two, which is crank. The link number three is connecting rod, which is attached to the fourth link, which is slider. And we have extended the portion of slider to make a cylinder. Okay, in which the piston of link 1 will do up and down motion, and you can clearly see this. If you move it, this arm, it will look like an hand pump. Okay, so the practical example of this fourth inversion will be a hand pump. Okay, how we are making the hand pump? Fourth link is extended in the form of cylinder, and to the first link we are attaching a piston. So indirectly we are trying to make a piston cylinder arrangement in between link 1 and 4, and we have extended link 2, make an arm for pumping the water uh, out of the ground. Are you getting it, how this is converted to hand pump? uh, can I proceed towards next slide? Yeah, in single cylinder, basically a single slider crank chain, we have just replaced one link of 4-bar chain with a slider. In order to make a double slider crank chain, we have to take a 4-bar chain and replace two turning pair with the two sliding pairs. Okay, then only we can possibly make a double slider crank chain. So basically, um, here this is, and oh sorry, let me just go back. So this is the first inversion. We are fixing link number one. Okay, link number one is fixed. Link number two and link number four are sliders. Okay, one is fixed, two and four are sliders, and three is a joint between them. Okay, or connecting link between them. So where you will use this will be used in an application called as elliptical trammel. Use the elliptical trammel. Elliptical trammel, like you can use it to generate the different ellipse. So look at this figure on right hand side, figure number B. You can clearly see this how this um, mechanism is used. So what we are doing is we are just extending this link 3. Okay, and so for example we have extended till this number C, and then just do the motion of it. Okay, if you move it, what will happen? This A will, if you try to bring it down, then it will bring down. A will come here, B will also slide down. So in so what will happen when this A will come to an extreme end? This C point will come here, okay, and then the C point will trace an elliptical curve. Okay, so whatever size of the ellipse you want to generate, you have to elongate this to that extent. Okay, you have to elongate it to that extent. And what is the equation of ellipse you will get here? X square divided by BC square. Okay, B to C is your um, um, half of the minor axis. Okay, and then plus y square divided by AC square equal to 1. What is AC here? AC is the major axis of this ellipse. Okay, BC is the minor axis and AC is the major axis. Okay, so try to think. If you want to make a circle, can you tell me where that point number C you have to keep, or what should be the possible case in that situation? How make how can you generate the circle out of it? Can you generate? That is the first question. Yes, yeah. So whenever we make AC equal to BC, so if that point C lies in between A and B, generator, um, and in such a way that AC is equal to BC, then only we will get this x square plus y is equal to AC square, for example, if AC equal to BC. Okay, this is the equation of circle, and this is the equation of ellipse. Okay, so we can generate the ellipse and circle out of this. So if you want to, so for example, A and B is fixed. Um, then let's say if you want to have, as you increase this point number C, okay, as you extend this point number C, your ellipse will get bigger and bigger. So whatever dimension of ellipse you want to make, you can make it from this arrangement. So this is the first inversion, and the application of it is elliptical trammel. We are fixing the first link. Can I proceed towards next slide? Okay. So if you want to write in between, and if you feel that I'm going fast, do not hesitate to ask me to wait. I'll wait till you write these all formulas, and then only I'll proceed. Okay. Yeah. The second inversion here is we are fixing the link number 4. Okay. So fixing link number 4 or fixing link number 2 is more or less same, because link 4 and link 2 are sliders. So either you can call that you are fixing the link number 4 or link number 2 here. Okay. So one of the slider is basically we are fixing. So any of the slider fixed, either 2 or 4, either link number 4 or link number 2. So for example, if you are fixing link number 1, link number 4 here, so link number 4 is slider. So in this case, we have made a slider in the form of a slot, a T-shaped slot. Okay, in the form of a T-shaped slot. And the link number 2 is kept, or it's moving inside that slot of link number um, 4. Okay. Um, okay, let me repeat it. Link number 4 is fixed. Okay, link number 4 is fixed, and link number 1 is made in the form of slot. Okay, link number 1 is made it in the form of T slot. Okay, link 4 is fixed. Link number 2 is slider, sliding in slot of link 1, and link number 3 is crank. So you can clearly see the fixed link is again slider. Okay, so we have a double slider crank mechanism. So this particular mechanism, we call it as, or this is Scotch yoke basically. Application of second inversion, and this figure is example of Scotch yoke. Scotch yoke is used to generate the sine and cosine function. Okay, so example, this whenever this the B point comes down at, let's say, 0 degree, we have this slot will move to an at one particular end. Okay, or at one particular location. As you move this slot, or as you move this crank, let's say by for example by 90 degree here. Okay, if this B point comes down, then this location of slot will come to somewhat this point, for example. Then if you again bring it here, then this location will come to here. Okay, um, and if you bring this um, try to draw. Okay, so this B point here, B dash, or B double dash, this B triple dash, and B 4 dash. Okay, so basically at B dash and B triple dash, we are at the center. Okay, whenever we are at a B triple dash, the end of this link number 1 is here. Okay, and whenever we are at a B double dash, the end of this link is somewhere here. So basically, let's say if you assume this as a 0 degree, or the 0 value. Okay, and for example this as um, okay, if you rotate it clockwise, for example, and then or okay, yeah, let's call it as let's say this point is -1 and 1. So basically, if you are at B triple dash and rotating it counterclockwise, if you come to this point, you will get, so basically you are rotating this crank by 90 degree. So corresponding to 90 degree, you are getting the value of the function as 1, then again 0, then again 0 at B dash, and then if you rotate this crank to B double dash, you will get the value of the function -1. So which function will rotate like this? We know that sine function will rotate like this. Okay, or behave like this. So similarly, you can generate cos function out of it, depending on just changing these values. Okay, so basically, the Scotch yoke, it will help us to generate these sine and cosine functions. Okay, is it clear? Uh, so yeah, I don't. So yeah, so we have one comment here that others take hours to teach inversions um, for single and okay. So I don't think there is any reason behind it. Okay, to teach it 5 hours. So maybe they are spending a lot of time in drawing the figures or all. I'm keeping the stuff ready here for you. The main intention is you should understand how that inversion is created. Okay, how you are making or how which link you are fixing and inversions you are making out of it. Okay, so if that is clear, then that's what is required from gate point of view. There no one will ask you to draw the figures or do the complete derivations of um, let's say why that in quick return with what quick return mechanism, why that time taken for forward stroke divided by time taken for return stroke is theta by beta. Okay, so from gate perspective, um, you should think like this mechanism logically. Okay, you should not like spend more time in your derivation part or uh, the figures. So that is the reason. Maybe you will find difference what you are saying 5 hours people are spending on single and double slider crank inversions. Okay, if you see previous year questions coming from inversions, either you will get questions mainly from let's say a quick return mechanism. Okay, or you will basically get the theoretical questions coming from inversions and their applications, or you will get uh, questions from acceleration and velocity diagrams of these different inversions. Okay, so these are the possible questions if you see previous year papers. So I don't see uh, any problem for you to solve them. Okay, is it clear till this? Any doubt? Yep. So in this case, in double slider crank mechanism, how many inversions will be there? Like in single slider crank mechanism, there were four. Here we have three. Why? The second inversion is same. Either you fix link number 4 or link number 2, you'll end up with the same inversion. So ultimately, the total number of inversions will be uh, 3. So the third inversion is where the link 3 itself is fixed. Okay, which is joint between link number 2 and 4. Link 3 of the first inversion is fixed. Okay, what was the first inversion? If you try to remember, this is the one slider, this is the another slider. Okay, and these were our guideways. This was our first inversion. Okay. So we have point A, we have point B. This is our link number 1. This is our link number 2, 3, and let's call this as a 4. Sorry, this one has 4. It's 2 I'll write inside to make it more clear. So now rather than fixing this first link, we are fixing uh, third link. Okay, so try to understand here the same structure we have drawn. Okay, link number 3 is fixed. Okay, here we have small slider. Try to understand through this figure, it's difficult to draw. uh, I have directly taken it from, I just googled it, and here also you have um, the fourth slider. Okay, fourth link is slider, second link is also the slider, third link is joint between them, and link one is basically a guide wedge. So what is this basically? This is how the mechanism will look like, but the practical application of this mechanism is Oldham's coupling. You know what is coupling? Coupling is used to join two different shafts. And why this Oldham coupling is special? Because whenever we have axial misalignment between the two shafts, look at this shaft number one here and this another shaft. So you can clearly see that these two axes are not aligned to each other axially. Okay, so in such cases you cannot use just normal flange coupling to um, um, let's say normal flange coupling with bolted joint. You cannot use it because that will not match the holes, and ultimately you will not be able to transmit power from this shaft to another. So in order to achieve the power transmission, we are using here Oldham's coupling. Okay, so try to understand here, this link 3 is fixed. So link 3 is more or less similar like this, and link 1 is made in a such a way that the slots are provided on the outer side of the link 1, and which will be fixed, or which will be which will be fixed in the slots of link number 2 and 4. Okay, so here this is these are the holes or hole slots we are providing, and here we are providing extension on link number 1, and that will fit into the uh, link 2 and 4, and ultimately we will make a coupling out of it. Okay, so this is more or less similar to this. We are fixing the link number 3, and 1 and 4 is in connection, and 2 and 1 is also in connection with each other, and that is achievable by this. So this is a very good example or application. You should know that Oldham's coupling we are using the cases where we have an axial misalignment. Can you tell me where you will use universal joint? You might have studied universal joint in maybe machine design, or yeah, mainly subject. What is the difference between universal joint versus this Oldham's coupling? Not particularly perpendicular axis. You are partially correct, Sean. But I would say that whenever you have axial misalignment, okay, your axes are uh, whenever you are having axial misalignment, you should go for Oldham's coupling. But whenever you have angular misalignment, for example, one axis is coming, one shaft is coming like this, and another shaft is somewhere somewhat like this. Okay, they are ultimately crossing each other. Here they will not cross each other. Okay, they are parallel. They are not crossing each other. That's why you are using this kind of arrangement. Okay, to match this axial misalignment. But in universal joint, they are crossing each other. Okay, or hook joint, you can say that. That is how you will make um, whenever we have angular misalignment. So basically one shaft is at one particular angle, and another shaft is, let's say, uh, not at the same line but at some other angle. In those situation, we can go for universal joint. Okay, so you should know that there are like small things like um, universal joint, Oldham's coupling, their applications you should know, and these kind of questions you can expect in exam, especially in match A and match B kind of questions. Okay, now is it clear till this? Yeah, I think that's all you should know, especially from this mechanisms chapter. Uh, we'll solve the questions at then. So then again, your concepts will get revised. Okay, so whatever we have studied till now, we will be um, recalling it before we jump on the problems. Okay, so that is how I want to teach you. Like we will just go through the theoretical part first, and once we start the problem from each topic, we will recall whatever we have studied in that topic, and then so basically we'll collect forms or um, just list down the concept which we have studied to um make sure that you are aware of it, and then it will be very easy for you to solve the questions. Okay, so in the meantime, like as I'm proceeding to the another chapters or another topics, you are supposed to go through the slides once again. Okay, and if you have some time, you can also go through the reference book. Either you can go through ss Ratan is good, mainly if it's fine if you just go through it, no need to refer any other book. Okay, but if you have any other book with you, you can refer that as well. Yeah, ultimately, what I'm trying to say is uh, just go through this recording or slides, and if you have free time, go through some reference book. Then it will be like a revision for you, and when we deal some questions, it will be very easy for us to understand it. So I'll open the different presentation now, because till now whatever we have studied is just uh, a background for your first point in your syllabus, that is displacement, velocity, acceleration, analysis of the mechanisms. Okay, um, so basically analysis of the plane mechanism is the topic. We have understood the mechanisms. Now we'll try to understand, we'll try to analyze them, um, try to find how the velocity of different links will look like, and ultimately how the velocity diagram and acceleration diagram will look like. Okay, yeah, so whatever we have studied is like it will act as like just a basic um structure or prerequisite, you can say, for the velocity and acceleration analysis topic. So you can calculate velocities and accelerations analytically as well as graphically. In exam they will, like in a university exam, you might have just let's say drawn the velocity diagrams and the acceleration diagrams on graph papers and cal with some scaling, and then you might have um, let's say uh, calculated the different velocities of different links by using that graph scaling and applying the scaling factor which we have used. Okay, But in gate exam, that is not the approach. You and they are not also expecting you to draw any diagrams, but diagrams are important here. We should know how to draw the velocity diagram, then only we will be able to understand, or will be um, able to make some conclusions out of it. So in this chapter, though I am drawing the diagram, it doesn't mean that like in exam they will ask you. Thing is that that is very useful for your understanding. Okay, so if you know the way to draw the velocity and acceleration diagram, then only we will be able to get familiarized with these concepts, and you will be able to solve these questions. Okay, so we'll try to understand velocity and acceleration analysis. So yeah, uh, let me try to think how can I give some brief introduction. I hope you are. I hope most of you have, or all of you have, done with the mathematics course. Please let me know if you are not. Are you done with maths course? Yeah. So some basic vector knowledge you having. Okay, like um, if we have, let's say, law of triangle of forces. In mechanics also you might have studied this. Okay, so addition of vector, um, triangle law. I hope you are aware of it. Let's say, for example, um, I'll just explain you here. Let's say this is point O, and let's say this is one vector velocity. I'll call it as a V. This point is a VAO, for example. Okay, and let's say this is from A to point number B here, velocity B. Okay, then closing side will be the resultant of this vector, correct, or addition of this vector, you can say VBO. Okay, so VBO, you can say it as a VBA plus VAO, correct. So V stands for velocity. If you just write in terms of, let's say, OB, if you just want to write in terms of OB, let's say, for example, or the points OB equal to OA plus AB. Okay, so this is uh, if, let's say, two vectors are joined one after the other, then their closing side of the triangle will be the resultant, but in opposite direction. Okay, so this is the law of triangle of forces in mechanics you might have studied, or this is the vector addition you might have studied in maths. So similarly, if you have more and more forces, law of polygon of forces you might have studied in mechanics or in maths. Let's say if more number of forces you are adding, let's say I'll take an example. Let's suppose a point O is here. Let's say this is point number A. Then one more velocity we have here. Let's call it as a VAO, VBA. This point is B. Okay. Um, let's say another. Let's say point C here, VBC. Let's say this point is maybe D, and this VDC. Then the closing side will be the resultant or addition of this. I'll use the red pen. Okay, so that is VDO. VDO in this case. For VDO and OD you can write later is VDO AO plus V, BA plus V, CB plus V, DC, or you can write as OA plus AB plus BC plus CD. Okay, so these are just different forms of writing it. So if you add all the vectors, then the closing side of that polygon will be the resultant, but in opposite direction. So I hope you might have studied this in either in mechanics or maths. Um, this is similar as the law of triangle of forces in mechanics, which we study, and this is same as law of polygon of forces, which we study in mechanics. Okay, so if this is known to us, then it will be easy for us to understand how the resultant velocity, how the resultant acceleration of any link will look like. Okay, is it clear till this? Yeah. Then let's um, yeah. Okay, yeah, I'll just give one point at the same. Yeah, let's take it here. Before jumping into this a bigger example, I'll take a very small example first. Let's try to understand a link, a simple link. Okay, so this is a point number O, this is point number A. Okay, so this OA link you have, and you this is a turning. You can this is a turning pair basically. Um, here it is hinged, so you can OA is a rigid link, and you can rotate it about the fixed point O with an angular velocity, let's say for example omega. Okay, and R is, let's say, the length of this link. So for example, if you rotate it from this particular location to somewhere here, after rotation it will come to this somewhere here at this particular point. Okay, um, because you are rotating in this direction. Suppose you are rotating it to delta theta, a very small angle, and this point is coming to A dash now. So what is so this is a displacement, that is r delta theta is your arc basically, and in how much time you are making this displacement, let's say a small time delta t. Okay, so velocity of A, I would say, with respect to the point O, with respect to O means relative velocity of point A, because O is fixed here, so that is not moving. So with respect to that, I'm calculating the relative velocity, that is equal to this displacement, which is arc A dash divided by delta t time. Okay, velocity is equal to distance traveled divided by time. If it is a small distance, I can assume it as a line, right? So that is the reason I'm writing it like this. So what is basically arc A? R times delta theta divided by delta t. Okay, and whenever this delta t tends to 0, so basically this is, you can write it as r d theta by dt, you can say, or okay, d theta by dt, a small angle d theta, and time is dt. Then what is d theta by dt? D theta by dt is nothing but the change in angular displacement with respect to angular time is angular velocity. Change in angular displacement per in time, in that time, small time dt is angular velocity, that is r omega. So basically, you from this what we have calculated is r omega will be the velocity of this particular point A. Okay, and what is the direction of it? the direction of the angular velocity is perpendicular to the um, link basically. Okay, so for example, I hope I'll draw it here to make it more understandable. This is particular point, let's say O, this point A. So this is your VA. And what is VA? R is this complete distance. Okay. And omega is the angular velocity. So R omega will give you the VA. Yeah. Suppose if I take any point B here, which is at let's say some distance X, what will be the velocity at this particular point B? Can anyone tell me? Yeah, be omega X. Okay. So omega is constant, X is um, now smaller than R. Okay. So basically, and slowly as you come downwards, what is going to happen is basically your velocity uh, vector is getting smaller and smaller and smaller. Is it clear till this? So I have just explained how the velocity of a link you can calculate. Okay, so analytically you calculate is r omega and its direction is perpendicular to the link itself. That is what we have understood from this. Let's try to apply this to a four bar link mechanism. So a link, so in this case just point O was fixed. Okay, but in this case we have mechanism point A and D is fixed. Okay, so let's start with this point A. Point A and D is fixed, that is not moving. So you have to fix that point because you don't have any velocity of the point A and D is zero. Basically it's not moving. With respect to point A and D, we are calculating the velocity of other links. Okay, so for example, let's say we have a link. We got a question from Shruti here. Can we say the velocity of point B is less than at A? Yes, for this particular example, we can say because the x is smaller than r and omega is same for both points. So uh, the velocity of B is less than A, you can say. Okay, linear velocity at point B will be less than that of A. Fine. Uh, Coming to this question again, E and D is fixed point. I'm fixing it here. The link AB is rotating clockwise direction. So basically, the velocity will be velocity of A to B will be perpendicular to it. Okay, like this. And what will the magnitude of it? The magnitude of it will be AB multiplied by AB is the length. For example, AB multiplied by omega is your velocity of AB. Correct? Or VBA. Let's call it as VBA. So you can clearly see these two are parallel to each other. And that's how this line has been drawn from point number A to B. Okay. Similarly, what we can see is the point D is fixed. Okay, point D is fixed. And you should know that why I am drawing this in this direction, not in this direction, because you can clearly see here our omega direction is in this direction. That is the reason I have drawn in this direction. Okay, you have to be uh, though they will not to draw the figure in exam, you should be aware that you should understand why this is the direction I'm choosing it, because our omega is in this direction, so the point B linear velocity will be in the right hand side. So similarly, the velocity of BC will be perpendicular to BC. So I will draw a line parallel to this from point B. How will get point B? We know the length of this velocity vector, that is AB multiplied by omega. AB length is known, omega is also known, so you can calculate that from that particular point. Let's say we are drawing a perpendicular to line to BC, and from CD also you are drawing a perpendicular line. So this is parallel to this, and wherever it is cutting, you will get a point C. Okay, so I'll repeat, this VCD is perpendicular to CD, and VBC or VCB is perpendicular to BC link. We already know point A, D, and B. We are just drawing these perpendiculars from these points. Okay, and that's how we'll get a velocity triangle. So our final velocity triangle is this. Okay, is it clear till this? Any doubt? Okay. So forget about point F. I'm just trying to explain you about E, C, and D. Okay, we are not including F here. Just A, B points, A, B, C, D. Are you following till this? Hello. Okay. Okay. So try to understand how the stuff will look like if you make it little more complex. Just give me a minute. Yeah. Yeah, maybe this figure. Let's try to. So this is a slider crank chain. The previous example was for the 4-bar chain. This is a slider crank chain. So in this particular example, you can see that the point O and G is fixed. So I'm drawing the diagram from this particular point. The
Sir,
velocity.
sir,
Yes.
will you explain that point F later, or we can ignore it? Sir?
I Yeah. So try to first understand how it is drawn. We will be drawing the velocity diagrams in the question. So I'll explain you that later. Okay.
Okay, sir.
So it is drawn in the same way. Nothing is different. Okay. Um,
Means the link 3 will have same angular velocity, no, sir? We will take the ratio of velocities to the position vector.
yeah. So basically here BCF is you can say it is a constant link. So it's a shaded region, right? It means uh, it's a just a single link here. Okay, so just F is another point on that link BC, which is at certain distance. Okay, and in order to capture that, we have drawn these perpendicular lines again. So basically, CF is a line which is perpendicular to this FC. Then this vector. So this is how this is perpendicular to FC. This vector is perpendicular to BF, and this is um,
Sir, E was understood, sir, because you have given the logic of R and X, that corner point.
Yeah.
But F
So
also, F was
yeah, F also I'm trying to explain here. See what how you are calculating F is not any, let's say, any separate link. Okay, F is part of BC link itself. Are you following? It
yes.
it is like a link which is having three ends. You can say B, C, and F. But we are not connected it to anything. It's entire a rigid body, entirely it's a rigid body. So what we have to do is we just have to get the position of it, and you can calculate the velocity with respect to the point A or D only. So considering that reference, this is how it is calculated. How this point you got? So this point you have to get immediately, and this point you will get by drawing perpendicular to this line and perpendicular to this line. Perpendicular to BF you are drawing. I'll just use the red pen here to show you how. Okay, so this is for BF vector, and green line I'll use for the um, FC vector. Okay, so you'll get point F, and that will be the velocity of point F with respect to points A and B, because you want with respect to a fixed point. That is the reason behind it. Okay.
Okay,
Yeah.
sir.
Coming towards this diagram here, um, you can clearly see here it's a slider crank chain. OA is a crank which is rotating in clockwise direction. Okay, so the velocity vector will be in this direction, and this is VAO, and the value of it will be um, omega times AO. Okay, R omega basically. AO into omega. So you can clearly see we have drawn it here, a line parallel to that. Velocity of slider will be always in the direction of the motion. Okay, because we know piston is either piston will move in this direction or in backward direction. So if it is moving in, if your crank is moving in right hand side direction, piston will move forward, right? So in that direction, I am drawing velocity of the slider. Velocity of slider is also known. So you got these 2 points. Okay, just um, basically join a line passing through these points. That will be velocity of BA. So for example, even if you don't know the velocity of slider, you can just draw this line, extend it, and then draw a line perpendicular to BA, and wherever it cuts, you will get the velocity of slider. This is how you might have solved questions in university exams in your college. Um, but in GATE, that is not possible. You don't have graph paper for it or to solve. So either they'll give some standard cases like where the calculations are pretty easy to do, or they will give you velocity of slider, and then they may ask you to solve it for other quantities. Okay, uh, we'll see what kind of questions you can expect here, but as of now, is it clear how the velocity diagram for slider crank chain will look like? Are you getting that velocity of slider, why I have taken in the direction of the motion? Velocity of slider is in the direction of motion of slider. Whereas in case of a rotating link, the velocity was perpendicular to the link, correct? So this is a difference you should know, because we are calculating the velocity of that particular point on the link. In this case, all the points on the slider will have the same velocity. Is it clear till this? Yeah. Okay. So try to bring some now acceleration concept. So we have understood basic velocity concept. Now try to bring some acceleration concept. Okay, let's try to understand this point. Um, Let me try to draw link here. So whenever we have a rotating point, okay, on a link, let's say again we link OA. Okay, so say it is rotating. Now in this case, the point A will have two components of acceleration. Okay, the point A uh, will undergo two kind of acceleration. One is the tangential acceleration, tangential component of the acceleration, and otherwise the centripetal acceleration. So the accelerations are two here. One is tangential acceleration. You can call it as AT. Okay. The this will be as r times alpha. R is the radius or the length of this link. And what is alpha here? Can anyone tell me? What is alpha? Yeah, it's an angular acceleration. So we know angular velocity omega. The change in angular velocity with respect to time is angular acceleration. So alpha is angular acceleration, which is d omega by dt. So um, or you can call it as a theta double dot also. Omega is theta dot, right? Change in omega theta with respect to delta d theta by dt was our omega, correct? So the same approach here. Um, if you differentiation of velocity is acceleration, so uh, you will differentiate the angular velocity with respect to time. You will get an angular acceleration. Okay, so this is the tangential component r alpha, and it will be perpendicular to the position vector. Okay, so it is perpendicular and it's direct. This is the magnitude of it, and direction of this will be perpendicular to the position vector. Yes. Second kind of or second uh, type of acceleration is centripetal acceleration. Centripetal acceleration or radial acceleration also you can call it. Centripetal acceleration. No, yeah, better to call it as centripetal acceleration because it is, you know, these words centripetal and centrifugal. Centrifugal means away from the center and centripetal is towards the center. So this component of the acceleration is always acting toward the center of the rotation. So its direction is always acts towards center of rotation. Okay, and the value for this will be r omega square. R omega square. Okay, so for example, this particular link is there. How the acceleration diagram this link will look like is let's say this point is O, or let's take any point, and from that point you will calculate you will draw first the centripetal acceleration. Let's say you are drawing first, and then the tangential component to it. Okay, for example, like this. Okay, and then the resultant out of it is this is the resultant acceleration AC. Then acceleration, tangential acceleration, and the total acceleration. Okay, so they are perpendicular to each other. Total acceleration is sum of square of tangential plus centripetal acceleration. Okay, so this is how you can calculate the total acceleration in case of a turning link. Yeah, I can give you contact number. We have a message in group to share the contact. I'll share you here in chat box. Okay, so in case of any conceptual doubt, you can um, ask me, okay, through WhatsApp, or if you have any questions, like for questions, I would suggest you first put in our group, uh, WhatsApp group, and then someone will answer you if anyone have already solved it. But if you have any conceptual doubt, feel free to directly contact me on this number. Yeah. Okay. So this is the turning pair, and if we have a slider will have the acceleration. Okay, so like slider, you can imagine like an any body like which is sliding on a road or sliding on any surface. Okay, it will have, so acceleration will be um, in the direction of motion. If it is deceleration, is opposite to the direction of motion. Okay, so you should know that what the difference between acceleration and deceleration. If your velocity is increasing, you call it as acceleration. If your velocity is reducing, you can call it as a deceleration. Okay, so how it will look like in case of turn slide pair, that is the main question. So we know that how in turning pair, we understood how in turning pair how the acceleration, total acceleration you can calculate. In sliding pair, there is nothing to understand, like it is just in the direction, like acceleration is change in velocity with respect to time. um, if it is positive, you call it as acceleration. If it is negative, you call it as a deceleration. How how to understand it in the case of a turn slide pair, that is the main question. I'll go to the next slide now. uh, Write down heading turn slide pair. Okay, so we have a link. Okay, and on that link we have a slider. Fine, so let's call this point A, and we have, let's say, P and Q points. P is on link, and let's say Q is the same point but which is on a slider. Okay, I hope you understood point O, P and Q. The P and Q are in coinciding with each other, but in this figure, but P is on link and Q is on slider, and the slider is sliding on link, and this link also you are rotating, so it's a turning pair as well as sliding pair. Let's call it as a turn slide pair. I hope you understood. So this turning pair is turning with velocity omega, and it means angular acceleration alpha, and let's say the radius is r from this particular point. Okay. Yeah. Now let's try to understand in this case how the velocity and acceleration will look like. So this is point O. Okay, this particular point O. Um, the point P will have velocity in this direction. Okay, it's a perpendicular to link. You can clearly see here. So let's use a red pen. Okay, this is velocity of point P. We'll try to draw a line which is parallel to this. Okay, so this is a tangential velocity, and our slider is sliding in this direction, for example. Okay, so from this particular point, um, um, so okay, let's take this point for example. From here, let's say um, slider is sliding in this direction. Okay, um, velocity of slider. Okay, so and then this is the resultant velocity. You can draw it later. Okay, um, maybe it's more clear when I explain you through this what you can say the single slider crank mechanism rather than this. Okay, because here just a single link, but try to I think we have in the beginning of this chapter I have explained you uh, for uh, for a single slider crank chain how exactly uh, the velocity diagram will look like. Yeah. Okay, so you can call it as the resultant velocity. Yep. Now um, this is point P and Q. Okay, and this was our O. Now the main thing here is the acceleration. This is a little tricky. So we know that a turning pair has two acceleration. One is in the, let's say, in the centripetal direction. Okay, AC, that is r omega square. Then we have tangential acceleration. Tangential acceleration is r alpha. Okay. Um, yeah, and I would have joined these 2 points to calculate the resultant acceleration for the turning pair, but on that we have sliding pair also. Okay, so it's not that straightforward now, because slider will have some acceleration. So slider is sliding in this direction, so this is the acceleration of slider. But as slider is, so I'll draw this simple figure here. So this slider is here, for example, in at the beginning, and after some time, slider comes here. So it is accelerating on its own. On top of that, we are turning this link in the left hand direction or the counterclockwise, which is also forcing the slider to go away from the um, origin or away from the center of rotation. Try to understand. So it's creating a centrifugal force, so which is trying to push this slider away from the center, and slider also has some acceleration, so which is there. So not just acceleration of slider, but there is one more component of acceleration will generate, that is nothing but the Coriolis component of acceleration, because it is due to the combined effect of or you can say uh, so for example, if the slider is sliding on its own, then it would have been, let's say, at this location only. Okay, so this point moves here and this point moves here, so little bit of movement is here from, let's say, this distance is um, 2, let's say, and this distance is now little bit more than 2, let's say 3. But in reality, this slider is moving to somewhere here. This is the actual location of it. It means something else is also pushing it, correct? So what is that position gap basically? This gap is because of the Coriolis component of acceleration. Okay, it is because of the combined effect of turning of this um, link and the sliding of the block. Okay, and that is nothing but the Coriolis component of the acceleration. And I'll explain you that how to calculate it, and what is the direction of it. So, but basically in this case, the Coriolis component of acceleration will be in this direction. Rotate. So it's basically you have to rotate the velocity vector in the direction of um, um, angular velocity. This is the velocity vector of the slider, and if you rotate it in the angular direction, in the direction of angular velocity, the rotation, it will be here. So I'll draw. This is the um, Coriolis component of the acceleration. So let's call it as ACOR, and let's say this was your initial point. Then this is your resultant acceleration or a total acceleration. So I hope you understood here. I will explain about this Coriolis component, but before that, you should know that what is this AC, centripetal component of the acceleration for the turning pair. This is tangential component of the acceleration. This is the acceleration with the slider of the slider. Slider is accelerating with this acceleration, and this is a Coriolis component of the acceleration. Okay, what is this Coriolis component of the acceleration? We'll see. Uh, but are you following till this? Like, do you know like why um, another? At least you understood why this A Coriolis is considered here. Why a new acceleration is coming into the picture is because of the combined effect. Okay, so if you um, so if this piston is fixed on this link, nothing will happen. Okay, whatever position of the piston at this particular point, let's say this is the piston, the same at it when this link comes here, it will also at that location, but this piston is moving in this direction, okay, with some acceleration. So it we expect that it comes from this location to this location, some it will go a little away from the center. But this moment also will create some acceleration, because you can imagine, like if you tie um, let's say take a for example um, a stone, and if you tie it to rope and mm, uh, try to rotate it, so it's like a centrifugal force kind of force you can expect the stone will feel. Same way here, uh, some acceleration is uh, getting generated because of the combined effect of the acceleration of slider and the rotation of this link. Okay, and that is called as a Corley's component of the acceleration. And write down that Corley's component, Corley's Corley's component. Okay, so this is the acceleration which you can calculate by rotating the velocity vector in the direction angular velocity by 90 degree. Okay, so I'll just give you an example. So this is your turn slide pair, and this is your piston or slider. Okay, let's create all four possible cases. Okay, so for example, the slider is sliding in this direction. Okay, and in this case, slider is sliding in downward direction. In both the cases, you are rotating the link in counterclockwise direction. In this case, you are rotating link in clockwise direction. The slider is sliding away from the center and coming towards the center. Okay, so these are the four possible cases. I hope you understand till this. So what is the Corley's component of acceleration? Corley's component of the acceleration is given by 2v omega. As I said, it's the combined effect of the velocity of the slider and the omega, which is the rotation of this link. So 2v omega is the Corley's component of the acceleration, and you can the direction of this is rotate the velocity vector in the direction of angular velocity. So what is the angular velocity direction? It's a counterclockwise. So you rotate this velocity vector counterclockwise. Counterclockwise, if you rotate, how it will look like? This is how it will look like, correct? So this is AC A Corollis. Are you following it? In the same way, in the second case, our velocity vector is downward. If you rotate it counterclockwise, the Corollis component will be in this direction. In the third case, our velocity vector is going away from the center and our rotation is clockwise. So if you rotate it by 90 degree to clockwise, this will be the direction of the Corollis component of the acceleration. And in this case, it is clockwise rotation coming down. So if you rotate it clockwise, it will be this direction. So it is. Are you following it? These four figures. These are counterclockwise rotation. This is the clockwise rotation of the velocity vector.
Hello, sir. Am I audible?
Hello. Yes.
Sir, I thought how to find the direction of this Corollis acceleration, but I am not getting.
Yes.
How did you understand there is a Corollis acceleration in this setup? Like while we are
Yeah.
rotating this appetized, I think it. Like, is it
So
because the final point? Can you explain that once, please, sir?
yeah. Yes. Sure. So whenever in the let's say mechanism, or in the setup, we have the turn slide pair. Whenever we have a turn slide pair, in that case, Corley's component of acceleration will come. In other case, it will not come, because we have turn slide pair which is generating this Corley's component. It's a combined effect of velocity of slide and the angular velocity of the turning pair. So that is first point you should know. Okay, and irrespective of, let's say, if you first take this velocity or that, first take the um, let's say your sequence doesn't matter basically. Okay, if you add all this, the resultant vector will be the total vector out of it. You might have studied in the vector calculus, or vector addition. The sequence, it doesn't matter. So first you should take Corley's component, or then the uh, the acceleration of the slider. Ultimately you will get the same total acceleration. The sequence also doesn't matter. So from this, what you can see that roughly you can say that total acceleration will be
Sir, will the Coriolis force will be there? I mean, asking for the pseudo force.
um, so I don't expect that you Coriolis force, but you know that pseudo is mass into acceleration. Acceleration, if you know, uh, just mass into acceleration will be the pseudo. But I don't expect they them to, because they don't give you the mass of slider and all. So in this velocity and acceleration, it is only you can say um, kinematics part. It's not a kinetics part. We are not dealing with the forces and moments here. We are just dealing with the velocity and acceleration. Okay. A total, how you can roughly calculate is like basically it's a right angle triangle. Okay. Um, for this figure, I'll once again explain how I have chosen this Coriolis component of acceleration. The velocity of slider is in this direction, so I rotated it counterclockwise, okay, by 90 degree, and that's why I got the Coriolis component in this direction, and that is why we have drawn it here. I hope it's clear. And basically the total acceleration I can calculate by calculating the hypotenuse of this triangle, because of this is the right angle triangle. I know the base of this triangle is uh, centripetal acceleration minus acceleration of slider, correct? This is the base square plus height is Coriolis component of the acceleration. If you take a root of it, I'll be getting the total acceleration. Are you following this? Hello, is it clear to you all till this? Till the Coriolis component of the acceleration? Hello?
Sir, like the A total will be equal to Coriolis, like it should add that R alpha also, right? Coriolis acceleration plus R alpha would be there, right? If it is kind of a
Yeah, sorry. Coriolis component plus R alpha. Yes, correct. So this total height we have to consider, right? That is R alpha plus A Coriolis. Okay. So do this correction. So this is height square and this is base. Correct. Thanks for letting me know. Okay, I think if it is clear till this, then we will end our session here, and we'll again continue this part in the next class. Our next class is on Saturday. Okay, this Sunday we don't have class, so on Saturday we will see some more um, cases, like possible cases of velocity and acceleration diagram, and then we'll try to understand some other methods like instantaneous center method is also there, um, and which will also help to calculate the velocities. Okay, so that is what is planned for the next class. Okay, so thank you all for joining this class, and let's meet again on Saturday. Bye. Good night.